Have you ever felt that deep frustration when your phone is just charging at a snail's pace? Or maybe you've unplugged an extension cord and noticed it's weirdly warm? Well, these aren't just random glitches. They're actually clues to a powerful, invisible force that's at work in all of our electronics. And today, we're going to crack the code and find the single scientific rule that explains it all. So let's start with a classic pain point, the slow charging phone. You plug it in, you're desperate for a quick power-up, but an hour later, that little battery icon has barely moved. What is actually going on inside that charging cable? Or how about this one? You're using a really long extension cord, maybe for some power tools or even just holiday lights. You go to unplug it and you notice, hey, this thing is warm, maybe even a little hot to the touch. Why on earth is it generating heat? Now, at first glance, a slow charge and a hot cable, they seem totally unrelated, right? But believe it or not, they are both symptoms of the exact same fundamental principle of science. And if you stick with me, you're going to see exactly how it all connects. Okay, the culprit behind all these little mysteries is an unseen force that's at work in every single electrical circuit, and it's called resistance. So what exactly is it? Well, officially, resistance is the opposition to the flow of electrical current. The best way to think about it is like electrical friction, and we measured this friction in a unit called ohms, which is represented by that Greek omega symbol you see there. You know, the easiest way to picture this is with a water pipe analogy. Think of electricity as water flowing through a pipe. On the one hand, you have low resistance. That's like a big, wide-open pipe, right? The water just flows through super easily. But on the other hand, you have high resistance. That's like a narrow, gunked-up pipe that slows that flow down to a mere trickle. And if we could zoom in, what's actually happening is that the flowing electrons are constantly bumping into the atoms inside the wire. It's kind of like trying to sprint through a really crowded hallway. The more of those collisions you have, the higher the resistance. And this is affected by four main things: how long the wire is, how thick it is, its temperature, and of course, what material it's actually made of. So we have this force, this friction, called resistance. But how do we actually measure it? How can we predict what it's going to do? For that, we turn to the one law that basically governs all simple circuits. And this is it. It looks simple, I know, but don't let that fool you. This is Ohm's law, and it is the absolute bedrock of electronics. It tells us that voltage, which is the electrical push, is equal to the current, which is the flow, multiplied by the resistance, the opposition. Let's just quickly break down those three key players. So V stands for voltage, that's the electrical push or pressure. I is for current, that's the actual rate of flow. And R is our new friend, resistance, the opposition to that flow. So the push you've got is determined by how much flow you get, times how much opposition it's up against. All right, theory is great and all, but let's see how this actually works in practice. We're going to put this law to the test with a real-world kind of example. Okay, so imagine we've got a simple component in a circuit. We get out our tools and we measure a push of 12 volts across it, and we see a flow of 2 amps going through it. So the question is, how much opposition, how much resistance is this component putting up? Solving this is actually a really straightforward 4-step process. First, we start with our main formula, Ohm's law, V equals I times R. Second, we just need to rearrange it a little bit to solve for R, the thing we want to find. So that gives us R equals V divided by I. Third, we just plug in the numbers we measured, 12 volts divided by 2 amps, and finally, we do the math. 6. But 6 what? 6 ohms. That's it. That's our answer. By just measuring the voltage and the current, we were able to precisely calculate that invisible resistance. Pretty cool, right? So Ohm's law seems like this perfect, unbreakable rule. But, and this is where it gets really interesting, in the real world of electronics, some components, well, they don't always play by the rules. See, on the left, you've got what we call ohmic components. Their resistance is constant, it's predictable, and they follow Ohm's law perfectly. But then, on the right, you have the non-ohmic components. For things like the tiny filament in an old-school light bulb, the resistance actually changes as it gets hotter. And that means its behavior isn't quite so simple to predict with our basic formula. And this is an absolutely crucial distinction. Honestly, one of the most common mistakes people make when they're starting out is just assuming that V equals I times R can be applied to every single thing in the exact same way. The real key is knowing what kind of component you're working with. All right, we have covered a lot of ground here, from, electrons bumping around in crowded hallways to components that literally bend the rules. So let's wrap this all up with the key things you really need to take away from all this. So here are the key pieces of the code that we've just cracked. First, resistance, measured in ohms, is just the opposition to current. Second, the master key to understanding it is Ohm's law, V equals IR. Third, a wire's physical properties, its length, its thickness, the material, and its temperature, they all change its resistance. And fourth, remember that not everything plays by the rules. Some components are rebels, and their resistance can change. And now we can finally solve our original mysteries. That warm extension cord, well, it's long and probably pretty thin, which gives it higher resistance. And that resistance is turning your precious electrical energy into wasted heat. And what about that slow charging phone? That's a cheap, high-resistance cable acting just like that clogged pipe, choking off the flow of current to your battery.
So I'll just leave you with this final thought. The next time you flip a switch and you see a light bulb glow, you'll know it's not just making light. It's the visible result of this intense, unseen battle between the push of voltage and the opposition of resistance. And it's happening billions of times every single second. Makes you wonder, what else around you is secretly being governed by this one simple law?